So you can actually do set B of C and clear of C. Now the C again is hardwired in the opcode. Okay, so the first case C is not named explicitly. Okay, whereas set B with a bit, when it says bit, that actually indicates explicit bit address, and that's the bit address I was telling you about at the beginning, right? So it could be anywhere between the bit addressable region from 20 to F, or one of the special function register bits, right? So that the lower two, when it says bit, that actually says bit address. And so there are two ways then you can express setting the carry bit or clearing the carry bit. One is to use the two instructions above with a C. The other is to say CY, and that would refer to the bit address of the carry flag, right? That's a PSW.7. So one letter difference, they do exactly the same thing, but the top one uses a single byte. The bottom one uses 2 bytes. Because top one does not name the C explicitly. The bottom one names the CY, namely the bit address of the carry flag explicitly. That's why it needs 2 bytes. Right? Just like the A versus ACC. A is implicit, ACC is explicit. Right? So here it explains the difference. So you can see encoding. If you do set B CY, that makes the address of CY explicit. That's a separate byte. That's D7, right? Encoding for CY. If it's just C, then that's part of the opcode. So there, it just takes 1 byte. Okay. So there's the difference between implicit versus explicit addressing. Now you can also do move instruction on bits, and so you can move C to bit, move bit to C, but you can't move from one bit at an address explicitly to another bit at a separate explicit address. Just like move cannot take 2 direct addresses. Same thing here. So if you want to move from P1.2 to P2.3, sorry, you have to go through C. Move it to C and then move it out of C in 2 steps. And move cannot take a literal, like a #1, #0. Instead, you have to use set B or clear. That's just the way they design the assembly language. Okay, there's something to pay attention to. Again, right? So this is a difference between implicit versus explicit addressing. So when you do move something to C or move C to something, that C part is part of the opcode. It doesn't specify the address separately. Okay, so move of 2 bit addresses, that instruction does not exist on 8051. Now C can be used as a bit accumulator. So there are couple of ways to do this. One is you might use, this is what's called a polling loop. What that does is you're basically checking an input port to see, oh, has the value gone to high or low, right? And then if there's a change on the value, then you do something. Otherwise, you just wait and spin. And so one way to do this is you do set B P1.2 in both cases. You could do move from P1.2 into C and then JNC, right? To jump if the carry bit is not set, right? So, or if the carry bit is 0. So it continues looping as long as it's 0. And then when it's not 0, then it continues. It falls through. It's equivalent to the other instruction. That's JNB as opposed to JNC. Right? The C part refers to the carry bit. JNB, that requires you to name some explicit bit address. And so P1.2 is that refers to a bit address. So instead of doing a move into C and then testing C, you can have the jump instruction testing that bit at that address explicitly, right? So you save one instruction right there. So JMB P1.2 again. So that does the same thing as the one on the right, the one on the left. Okay, while we're at jump or conditional jump, you're gonna need this for part of your assignment. Now, so I just showed you one example where you do the jump based on either condition code or based on an explicit bit, right? Because the bit can only be 0 or 1. You can have either jump if the bit is true or jump if the bit is false. So the end part makes it jump if it's false or 0, right? So JC, JNC, JB, JNB, and all that. And so here I'm showing the encoding as well. So now, so JC is 40, and the target is represented as an offset from the program counter. Actually, the address of the next instruction plus the so target is the address of the next instruction plus the offset. The offset could be positive, it could be negative, right? JNC again, that's just a different encoding for the opcode, but offset is the next byte. And then JB, well, or JMB, there's the opcode followed by the bit address, which is a byte, and then followed by the offset, which is another byte. Okay. So as you see, JC, JNC, they are 1 byte less than the JB, JMB due to the not having to name the C bit. Okay. And there are these bit moving instructions. So CPL for complement, that means turn a bit from 0 to 1 or 1 to 0. Just flip it, right? CLR sets it to 0, set B sets it to 1. And then if you have to name the bit, then that occupies 1 extra byte. If it's the C version, it's just 1 byte. Right? You don't have to name it. And then there's move C to P0.3 or move P0.3 to C. Then yeah, both will occupy 2 bytes. Right. So again, just to see how it's related. So now accumulator itself, A, turns out to be bit addressable as well. So you remember A. If you see A, then that's implicit addressing. That means part of the opcode. If you see ACC, that refers to the address of A. And that's at the E0. And each bit of the accumulator also has an address. So you can say ACC.0, ACC.1 up to ACC.7. And those would have the bit addresses of E0, E1, E2 to E7. Okay? And so this actually can be useful sometimes. And also, remember if you have to push or pop with the accumulator, you can't say push A or pop A. You have to say push ACC or pop ACC. That's because push or pop require an explicit byte address. And so if you just say A, and it says, well, you want it to be part of the push or pop instruction. Sorry, that doesn't exist on 8051. So you have to give the ACC, which says that's the byte address of that accumulator. And bit addressing in the accumulator, right? So you just you can say JB, JMB, with the ACC.0, ACC.1 or something, right? Okay. So now, how is that useful? Well, because if you can check the individual bit, that actually can tell you quite a bit about the result, because the accumulator stores the result of a computation, right? So if you look at ACC.7, that's actually a sign bit. So it allows you to determine if something is negative or not, right? If ACC.7 is 1, that means it's negative. Also, you can tell if something is even or odd by looking at ACC.0, right? Because if it's 0, that means it's even. If it's 1, that means it's odd. So, yeah, just by looking at certain bit, it can be pretty useful. Bit address versus byte address. Okay, so move instruction, well, depending on if you say A or C, the other address will be interpreted to be either a bit address or byte address, right? You understand that? So if I say move something A, because A is part of the opcode, that makes the 5 there a byte address. If I have an instruction that has move something C, then that address, like the 5 there, that's interpreted to be a bit address. Does that make sense? Okay? So it's very context dependent. Okay? So again, just one little character difference can mean something entirely different. Okay? Oh, OV flag. Oh, that's PSW.2.